We are in the titration notes, example number 5, which is still a weak acid, strong base titration. So let's remember what our curve looks like. Remember, this is the initial concentration, and the initial pH will be a weak acid problem. This is the half equivalence point here. Remember, this little bit of in the beginning is because the free H pluses are being consumed. This is called the equivalence point, and the equivalence point is when there is no more H plus or OH minus, and all you have left is the conjugate base of a weak acid. That's why you expect the pH to be greater than 7. So let's label these. This would be the initial concentration. This is the half equivalence point, and this is the equivalence point here. So in the beginning, it is a weak acid ice problem. At the half equivalence point, pretty straightforward. It's where the pH equals the pKa. At the equivalence point, it is a weak base ice problem. So let's review the general form for a weak acid and strong base titration. Remember, an acid acts like an acid by donating a proton. So what's going to happen is the acid here is going to give a proton to the base. On the other side, the base is going to have a conjugate acid, and that's what he's going to look like after he takes a H plus from the acid. And the conjugate base is what's left over of the acid after he gives away an H and a plus. So this is a general form. Our problem states that a 0.700 gram sample of an unknown weak monoprotic organic acid HA is dissolved in sufficient water to make 50.0 milliliters of solution. So let's write down what we have. We have 0.700 grams and 50 milliliters. And it is titrated with a 0.155 molar NaOH solution. It says a pH of 5.85 is recorded after the titration of 12.5 milliliters of base. The equivalence point is reached after the addition of 25 milliliters of base. So if it takes 25 milliliters of base to neutralize it, that means that 12.5 milliliters is actually the half equivalence point, correct? So that's an important piece of information here, is because the pH at the half equivalence point was given to us in the problem of 5.85. Part A asks us, calculate the moles of acid in the original sample. Well, let's see. It is monoprotic, so that means that it's going to be 1-to-1. So 1 mole of HA requires 1 mole of OH minus. So let's calculate how much OH minus do I have? Well, I had 0.155 moles of OH in 1 liter of solution, but I don't have 1 liter. I have 25 milliliters, 0.025 liters. So that tells me that the number of moles of OH is 0.003875. So that's how many moles of OH that I have at the equivalence point. That's how many moles of acid I have. It is a 1-to-1. So if 1 mole of acid takes 1 mole of OH minus, then 0.003875 moles of OH minus takes 0.003875 moles of HA. So that's how many moles of HA I have in my container. It'll also be the number of moles of H plus I have in my container. It'll be the number of moles of A minus I have in my container. So that is also the number of moles of my weak conjugate base that I'll have at equilibrium. So there's the answer to A. B says, calculate the molar mass of the acid HA. So molar mass, we have to remember, is how many grams there are in a mole. Well, we just calculated the number of moles, and we were given the number of grams of 0.700 grams in 0.003875 moles. So my answer to the molar mass is 180.65 grams per mole. If you remember when we did gas density, we were looking for molar mass too. And we were also doing that when we were doing solution stoic. And we were also doing that when we were doing general stoic. So you can expect them at some point in time to ask you the molar mass. Just remind yourself that molar mass is grams per mole. And you say, I got to calculate the number of grams. I got to calculate the number of moles. Figure out what's given to you and what you can calculate. C states, calculate the value of the ionization constant Ka of the acid HA. Listen closely to this because you can make this really, really difficult by trying to figure out the concentration of OH minus, concentration of HA, the concentration of A minus, or you can make it easy on yourself and recognize that we have the pH at the half equivalence point of 5.85, and that's equal to the pKa. So in order to get the Ka, we would do inverse log of the negative Ka, and your calculator, it will say 10 to the negative 5.85, and that gives you an answer of 1.41 times 10 to the minus 6. D states, what is the concentration of the original 50 milliliters of solution of HA? Well, now we're going to do exactly the same thing as we did for molar mass. Remember that when they ask you for concentration, they're asking you for molarity. And molarity is moles over liters. We calculated the number of moles of 0.003875. And that was in 50 milliliters of solution. So the original concentration of this is 0.0775 molar. Let's also look up at the top. You could have done, this is another way to solve this, the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Remembering we can only do this if they're 1-to-1. If you have a diprotic acid, you have to account for the number of moles too, which you can add that into this formula if you want to. But this is 1-to-1. So if you plug this in, you would plug in this for the base, for the molarity and the volume, and this for the acid, and solve for the molarity. If it takes half the volume of base, then you expect for the concentration of the acid to be half as much, which is exactly what we calculated, so that makes sense. Now let's go on to E. E is, what is the pH of the solution at the equivalence point? Remember, we talked about the fact that that is a weak base ice problem. So we have to first figure out what Kb is. Remember, Kb times Ka is always equal to Kw. So Kb is Kw over Ka. Remember, these are all in your reference packet, so make sure you know where these formulas are in case you time passes by and you forget. Ka is what we calculated in C of 1.41 times 10 to the minus 6. So Kb is going to be 7.09 times 10 to the minus 9. Remember, that is x squared over the concentration at the equivalence point. So let's figure out that concentration, remembering that concentration is moles per liter. We calculated the number of moles of HA. Remember, the number of moles of HA is also the number of moles of A minus. The A minus didn't go anywhere. So 0.003875 moles. And let's go back up. What is my volume at the equivalence point? 75 milliliters, so 0.075 liters. That gives me a concentration, which you know this is a dilution problem, so the concentration better have gone down, of 0.05167 molar. Not really worrying about sig figs right now. So let's put my concentration here now. So you've got that 7.09 times 10 to the minus 9 in your calculator. Do a quick times 0.05167, enter. Then you can do second square root of second answer, and that gives you the value for x of 1.914 times 10 to the minus 5. This is where we have to be careful because Kb tells us when we get the value for x, that's not going to be the concentration of H+. It's going to be the concentration of OH minus. So when I do negative log of x in this case, it's going to give me the POH, which is 4.718. That gives me a pH at the equivalence point of 9.282. If it is a weak acid, strong base titration, make sure that your pH at the equivalence point is in the basic range. So let's add this to our titration curve, 9.282. And that's the answers to all the questions in example number 5. This is only a little bit different because they gave us everything we needed to know about OH and asked us to backtrack to find A- and HA.